In this video, I'm going to show you how to do building instance segmentation using the open source GeoAI Python package. Instance segmentation means that for each object you're going to detect, it's going to get a unique ID. It's different from the semantic segmentation that all the pixels belong to that category is assigned as one class. And it's particularly challenging if you were trying to detect some object that they're adjacent to each other. In this case, if building, for example, they're adjacent to each other, then semantic segmentation might not work very well. In this case, we will want to use the instance segmentation. First, I would like to show you what the result looks like. As you can see from here, we are going to do the building detection. So each individual buildings has been assigned kind of a random color. And so this is the result we are going to get. So you can see we are going to detect all the buildings, and then each building, it doesn't matter if they're adjacent to each other or they are separated. We will be able to get them individually, and also you're going to get all the geometric attributes. For example, how many buildings, what's the size of the buildings, what the distribution, and also the geometric properties. We're going to get that easily with the Python package. So first, let me show you where to get the notebook examples. You can go to the OpenGeoAI.org website, and then on the left side, go to examples, scroll down and find this one, train instance segmentation model. Once you click, then you can either run this one using Google Colab. Just right click and then open this one in Google Colab. Make sure you change the runtime type to T4 GPU. So if you click that and just switch to T4 GPU, click save. After that, you should be able to install the package by uncomment this line, and then you'll be able to follow through one by one. So just click the button, you'll be able to run and execute to install the packages and then execute the Python source code. Alternatively, if you already have GPU and you have installed the package on a computer, then you can download this one to a computer, just right click, save as, then save this one to your local computer. So just in the pop window, just click save. Then you'll be able to open this one in your Jupyter notebook or Jupyter Lab. Okay, so I have this one open. Now I'm going to clear all the output, and I can show you from the very beginning how we're going to prepare the training data, and also how to train the instance segmentation model, and then run the inference on the data. We're also going to evaluate the performance of the model. So first step, we need to import the library. It's very easy. Just import GeoAI, shift enter. You're going to execute this line. It takes a couple seconds. It's going to import all the dependencies needed for the GeoAI package. And then we're going to download some sample data. So this is the same sample data we have been using for other tutorials. So we're going to use this NAIP, National Agriculture Imagery Program, RGB 3 channels. We also have a vector dataset, basically the building footprint covering the area. We also have a testing data. So we basically have 2 images and 1 vector. So just pointing to the URL, and then you can execute to download the dataset. I have already downloaded it, so it's going to be just showing you that the file already exists. If you're new to run this notebook, then it might take a couple seconds to download the data. It's pretty small dataset, so it should work pretty well. And after that, you can just get the some of the metadata for the raster. So just get raster info. It's going to show you the width and height of the imagery, and also going to show you how many bands in the imagery. You can also see the spatial resolution here, 0.6. That means it's 60 centimeters, so it's pretty high resolution. And so also you can visualize the data interactively. For example, just this one, view vector interactive, and you can use the vector data. Also the raster data is the background, basically the base map. So just execute it. You should be able to see the vector data, and then with the raster imagery over there on top of that. So this is basically just one simple data set, the raster imagery and the building. As you can see, if you have your mouse, you'll be able to see the class. The class represents like building, so it's only had 1 column. So this is a vector data set with just 3 columns, the unique ID, the height, and also the building, the class, the building type, and that's it. So we're going to basically train our model on this data set, and then we're going to apply that to a new data set. So you can turn the layer on off. This is all interactive, very easy to do, just one line of code to see what the data looks like before you try to train the model. Okay, so once we have the model, we can also have the dataset. We let me see, right now it's a little bit buggy. Let me clear the output and then run again. It's a bug of the Jupyter Lab. So let me open this one more time. So hopefully it will be working. Control S. Yeah, I think it's still something is wrong. Let me quickly fix it. Okay, so now it should be working. So let me quickly rerun all of this. It should be pretty quick. And then just view the vector data again, and then we can view the testing data set. So now the scroll should work, okay. And then view the raster data set. Oops, I think I might need to restart the notebook. 1 second. All right, so I have restarted my Jupyter Lab. Now it works properly. This is the testing data set. So we're going to train our instance segmentation model on this raster data and vector data, then apply to the new data set. So you can see the building, basically the spatial pattern is quite different. So the training data that we have is quite homogeneous and is also quite organized. Compared to this one, it's a little bit more complicated. You also have a lot of trees. The color, the size are kind of varied quite a bit, but it's going to do pretty decently. So let's proceed to the next step. We're going to create the training data. As I mentioned in some of the previous tutorial, if you're trying to do deep learning, we need to create image chips because we cannot fit the entire imagery and also vector data into the model. We need to create image chips. So the GeoAI package has this one single function, allows you to create image chips. Just export GeoTIFF tiles and specify where you want to output the data. So the input raster is our training raster, and the output here, also the in-class data is the vector data set. So basically it's the building footprint. Also, you can specify the tile size and also the stripe. So the tile size is basically the size of the image chip, and the stripe basically is the moving window. So it's 512, and then you're moving to 56 each time. That means it's like 50% overlap, okay? Also the bar for radius, this one we don't really need it for polygon data layer. Usually you don't want to do the bar for, but for linear features like roads and street network or power lines or something like that, if your vector data set is just a line, then you might want to do the bar for. Otherwise, you might get some disconnected features that might not be ideal. And so that's it. Just run this one. It's going to run through the whole process to show you some of the basic metadata information, how many bands, and also how many image tiles you're going to get. So you're going to generate a total of 36. With feature 36, that means 100% of the image tiles contain some buildings in that. Okay, and if you want to see the data, you certainly can. You can click the upper left corner and then look at the directory. So this is called buildings instance. So let me find this directory here, and it's going to create two directories. So the images, right? So all the image types here. This is basically the training data set. You can also look at the label. So it's the corresponding building footprint. And we provide a vector data set, but it has been automatically converted to raster mask. So it's one-to-one relationship. One imagery, you have one label, one other imagery, have another label. So in total, we have 36, as you can see from here. So this is our input data set. With that, now we can start training the data. So different from the semantic segmentation that each pixel is classified as 1 and otherwise 0. Sometimes if you have two buildings that are adjacent to each other, they're supposed to be two individual buildings. If you're using semantic segmentation, they are going to basically merge together as a single object. So it's kind of building complex, and that might not be what you want. In this case, you certainly want to use the instance segmentation, and specifically under the hood, we are using the mass RCNN. So this is a popular instance segmentation model that combines fast RCNN and then FCN and also ResNet 50. We have some parameters here allows you to customize if you want to, but you can just use the default parameters. So call this function train instance segmentation model, provide the image directory. So as I mentioned, show you earlier, we have all the images. We also have the labels. So these are the data that we generated from the previous step. Also, we need to specify where you want to save the model. So the output. After that, these parameters are similar to the one when we try to train the model. So the number of classes is 2. That means if 0 is background, 1 is building. We have 3 channels, so this 3. The base size equal to 4. It's how many images you want to fit into a model. So each time we put 4, if you have a larger GPU, you can train this one to a large number. So the smaller the number, the faster, but it's the larger number of batches that you need to have. And we want to train epochs. In general, you want to train maybe 20, 30 at least. But to save some time, we're just going to train 10 epochs. And then the learning rate 0.005. Val split basically just 80% for training, 20% for validation. And so let's just run this one to see how it goes. Minutes, you're going to find some metadata information here. So we have 36 image tiles and 36 label tiles. We have going to train a total of 10 epochs. And for each time, because we're only feeding 4 images in there, we have 36. So you're going to basically have multiple batches. What you need to pay attention here is the training loss, validation loss, and also the IOU. The IOU is probably the most important, is that you want to figure out what's the overlap between your prediction and the ground truth. So the higher the better. The value range from 0 to 1. 0 means it's kind of random, so your model doesn't predict anything. If it's 1, that means 100% overlap. After 10 epochs, you can see the IOU is 0.81. It's not like perfect, but it's decent, right? We only trained for 10 epochs. It only took a couple seconds. We already achieved 81% over that. Like I said, in reality, you want to train that a little bit longer for more epochs, 20, 30, 50, or even 100, depends on the data set that you have. Once we have finished training the model, we can find the model in the output directory. So building instance and then the instance segmentation models. So if you want, you can go to the your Jupyter Lab, your local directory. You'll be able to find this one here, instance segmentation model. And these are basically the 4 files that have been generated. Usually, we're just going to use this base model.pts. This is the one that contains all the model parameters. So we can directly use this one to run instance segmentation model on the dataset. So now we are ready to run the inference. We are going to basically pointing to the base model, as I mentioned earlier. Also, you need to specify the file path, basically the prediction where you want to save it. Once you have that, just call this function instance segmentation, and that's it. So the input file path is your testing dataset. So the one that I showed you earlier, where you want to save the output mask, also the model path. Then other parameters are pretty much the same as the one that you set when you try to train the instance segmentation model. So it's 512, my 512, overlap 256, and then the confidence level. So this is the only one you probably want to customize. You can also customize the base size, but the threshold is the one that you want to control. So in general, the value going to range from threshold, going to range from 0 to 1. The higher, the more conservative or more selective, but you might end up with a lot of missing objects that you're supposed to detect. The smaller the value, the more object you want to detect, but you might have a lot of false positive. So you need to play with this one. By default, the value is going to be 0.5. So it's going to basically run the instance segmentation model. And for each instance, it's going to have a probability. So it's the average probability within that object. And if the average is greater than 0.5, then it's going to be extracted. So in this case, we're going to set 0.5. And so see how many? We have 1,009 buildings within this testing imagery. Okay, once you have this, now if you want, you can adjust it, the parameter. If there's too many, of course, you can visualize the data first if you want to, but we can also just run this one. So I can set the threshold to 0.7. That means I'm going to increase my threshold. So in this case, you should expect to see a smaller number of buildings. So after this one, we have 935 buildings compared to the one earlier have over 1,000, so 1,009. So it's like a little bit 70 buildings less. It doesn't mean always that you want to get better accuracy because you might accidentally remove some real buildings. So you do need to verify before you run the basically the confidence threshold. So assume that okay, the earlier one using 0.5 is better. Now we can basically regularize the buildings. Regularize means we're going to basically convert the raster to vector, and then we're going to rectangularize because if you're just using the original raster to vector, you're going to end up with a lot of pixelated edges around the buildings. So for building detection or solar panel or some other kind of regular object, usually you want to call this function or orthogonalize. Then it's going to convert your raster dataset to vector and then simplify a little bit. Okay, so now it's done. You can add some geometry properties. The reason we want to do this step is to calculate the size, the orientation, and also the elongation, for example, some of the critical attributes, because later if you want to filter those objects, these attributes, the matrix might be quite helpful, because if you detect a lot of buildings and then there's some like tiny buildings, if you know the minimum size of a building like in the region that you're trying to detect, then you can filter out all those smaller buildings. Anyway, so we have finished all the calculation. Now we can start visualize the data. So first step, let's visualize the original raster. And this is the one that I showed you at the beginning, right? So we have this testing data set. And so the reason why you see the random color, because here I specify this CMap tab 20. That means I use basically assign one of the 20 random colors to each instance. And if you see from this here, they all look very colorful. Although in this region, you still see a kind of a lot of buildings, basically they're separated quite nicely, but you do see some like buildings that come kind of close to each other and they are still being separated. So if you see this one, it's actually pretty good. Of course, this one, it doesn't work very well because the model that we train on the imagery does not really have some like large buildings, so it's probably going to miss some of those. You might need to adjust the threshold to a smaller number, then you will probably detect those large buildings. So that's kind of limitation. Like I said, this is just demo. It's not going to be give you a perfect model, and you do need to train a little bit more and on more data, then you will get in general get better result. But this is still pretty decent. We only train for a couple minutes, and then we can run the inference on this data set. So you can see almost all the buildings have been extracted. Of course, there will be some false positive or false negative. That's normal. You just need to refine a little bit. Once you have this raster data set, you can also visualize the vector data set. So we're going to overlay, for example, the vectorized results. So this is basically the raster data set, and this one is the rectangularized or regularized building footprints. And it's going to look so much better than just the raster. So here, there's some missed buildings here and there, but overall, it looks pretty good, right? So this all the buildings that have been detected. You can also turn the layer on off to see the building footprint. And there might be some false positive. So in general, for example, if the buildings are very tiny, you can actually filter it out, because if you have your mouse here, you'll be able to see we calculate the geometry properties, right? So you can get the size, the length, the perimeter, the bounding boxes, and also orientation, everything. If you already know some typical matrix for the buildings in that region, then you can either filter out by area or by elongation, right? Elongation means is the long axis divided by the short axis. So that means how does it look like if this low value is very big, that means it's more like a linear features, and that's less likely to be a building, then you can filter them out. So but you can plot out basically the spatial distribution or the histogram, and to see in general what it looks like, then you can filter out those outliers. So this is why the geometry properties can be quite helpful if you want to filter out some of the false positive. For example, I know that in this area, all the buildings, for example, in general is greater than 50 square meters. Then we can just set this one, area square meters underscore square meters greater than 50. So in this case, we're going to filter out some of the smaller buildings. So run this one, and then we can visualize them again. You can certainly see some of the smaller buildings. Anything smaller than 50 square meters will be removed So in this way, we probably remove some false positive, but be careful, don't just use a single threshold, because sometimes it might detect a small object as part of the big buildings. So if you use the threshold, it might also remove some of those. One good way to do this is to actually show those buildings, like for example, less than 50 before you remove them. So just go through quickly to see if some of them are real buildings. Then you might need to adjust the parameter a little bit. So this is basically just the color placement. As you can see, we have the kind of a color. Upper right corner here, you should be able to see the legend, basically the color ramp. Shows you the blue color represents smaller buildings, yellowish color represent larger buildings. So you can certainly see on the right, you have some of the larger buildings, and most of the buildings in the residential area, they kind of are pretty small. So this is how you go from training the model to running inference on the building, and also do some post-processing to generalize all the building footprinting. So we still have, you can see here, we still have all the attributes. And the nice thing about this is now each, you can see the value, basically the first row, that one shows you basically the ID. So right now each building has a unique ID compared to the semantic segmentation. Is pretty much all the building that's treated as one class. You don't really have, you cannot really distinguish between different buildings. Okay, so with that, now the last step, we can create a split map to compare the data side by side to see how it performs. Now we have all these building here, and we have the imagery in the background, and this is how you actually do the comparison. So if I zoom in, these are all the buildings. The red color represents the building footprint. As you can see, it looks pretty decent. Not bad, not perfect. Like it's not never going to be perfect, because we only train on a limited number of data sets. And there's also a false positive here. This one is definitely not building, but you can see it's kind of gets confused. You can sort of remove it, like if you combine with some, for example, digital elevation model. If it doesn't have any height, it can be probably removed. So you do need to have some post-processing to actually remove some of those buildings, and there are also some missing one. I guess you need to just set a threshold to maybe 0.3 or 0.4. It might detect some of those. The reason why it doesn't show up is because probably the confidence threshold is a little bit too high, so they don't show up. If you set it to a smaller one, then it will show up on your imagery. Like I said, this is a demo. It's not perfect, but you can apply it to your own data set. If you have more training data, good quality data, this is going to give you a pretty decent result. Lastly, we can show you the performance. So this is something you want to see. Earlier, when we train the model, we already see that the training loss is decreasing and the IOU is increasing. Is a good thing. And this is something that we want to see whenever you are training the model. You want to have less and less loss and higher IOU. That means your model is performing the way that we expect, and it's a good thing. So we only train for 10 epochs. It reached like 0.8, so basically 80% overlap between your prediction and your ground truth. It's a good thing. And that's pretty much it. And this is the whole process. Like I said, it's very generic, so you can replace the data with any data set you want, as long as you have a raster and then you have a vector data label, or you can also have multiple raster, multiple labels, multiple vector data set. Either one works fine. So you can just use the export GeoTIFF tiles, then it's going to basically figure it out, create the image chip for you. And lastly, some basic information here. When you want to use semantic segmentation, when you want to use the instance segmentation. In general, if you don't really care about like adjacent objects or large objects that are adjacent to each other, then you want to use the semantic segmentation because it's faster, certainly much faster than the instance segmentation. Instance is going to give you individual labels, and it's very useful if you want to separate objects that are adjacent to each other. You want the individual building rather than building complex. Then you want to use the instance segmentation. The downside is that it's going to be a little bit slower compared to the semantic segmentation. But as you can see from the video, it's actually not a whole lot slower than that. So it's pretty decent. And this is how we get from training the data, running the inference, evaluate the performance, and then you can also do some post-processing on the data set. And Lastly, there are some batch processing. If you have multiple images, you want to run the instance segmentation, you can call this instance segmentation batch. Then you can point into an input directory. Once you train the model, you can run inference on multiple images, just calling one function. You can also do a looping, but this one function gives you kind of a shortcut, allows you to do that. Also, if you have multiple channels, so the example I show you only have RGB, but you can certainly run it on multispectral 4, 10, it doesn't matter. So all you need to do is just adjust this parameter and channels. So if you have more, then you specify the number here. Other than that, other parameters are pretty much similar. So this is how you can adjust this one to do multispectral data instance segmentation. So it's very powerful, it's very flexible. Try it out. And if you run into any issues, feel free to leave comments down below. I will make sure to reply to every comment. And I hope you find it useful. I will see you in the next one. Take care.